Thank you. Thank you to the organizers, not only for putting up a really wonderful conference, but also for giving me a much-needed vitamin D cure to survive the winters in Pittsburgh. This is really great. So, for something completely different, experiments in cosmology. Oh, sorry. Do we have presenter view on this? In any?
What is presenter view?
Where she can see what's
Maybe? Here? Is that a feature of PowerPoint?
Aha, there we go. Perfect, I got it.
Impressive.
Sorry.
So yes, we do.
Yes, we do, sorry. Sorry, small technical. So yeah, something, oh yeah, okay, here we go. Lambda CDM, we all know and maybe love it, maybe not, from the last couple of days. It represents the evolution of the universe, and as you know, it's quite successful as a phenomenological model, but it leaves open many questions, right? And there's recently been quite a few attempts, when I say recently, I mean 4 decades at least, at trying to answer some of these open questions, for example, related to the nature of dark matter, dark energy, etc. And some of these experiments have been happening in the labs on Earth, right? So here you have some examples. There's the LZ experiment that's looking for dark matter particles in direct detection experiments. There's the ADMX experiment at the University of Washington, which some of us visited last November. There's, of course, I just put Atlas on there, but there's lots of dark matter searches happening at CERN. For a while, there were some atom interferometry experiments happening on dark energy, but I learned last night that apparently at the previous dark energy conference, it turns out that they don't work, but I don't think that's a problem for what I'm going to say today. Anyway. So, it's kind of interesting that these experiments are happening because it doesn't seem at all plausible that they should be answering the questions that they set out to do, right? We're looking for dark matter, for example, at CERN, but one of the few things we know about dark matter is that it's not anything that particle physicists so far have managed to find at CERN, right? Similarly, the atom interferometry constraints on dark energy, initially, right, one of the few things we know about dark energy is that it has effects on the large-scale expansion of the universe. So it's really weird that you would be able to constrain it using like experiments, I don't know, the size of this room, even smaller, right? So this seems kind of weird. And so the question that I want to answer is sort of like, how can scientists justify their use of a particular method to investigate a given target, especially in light of these sort of puzzling experiments that we see in cosmology today? And so my goal for today is, first of all, answer that question, and the way I'm going to do that is I'm going to lay out 2 different structures that I think commonly underlie how scientists answer this question. One that's very common, one that's less common, but that seems more prevalent in these experiments that I just mentioned. And so by answering that question, I hope to achieve a couple of things. First, just help us understand how this is possible in the first place. But I think, and this is maybe more for the philosophers in the room, it also can shed some new light on some of the existing debates in philosophy of science, for example, related to robustness. Okay, so here's the plan for today. I'm going to give some terminology, some terminological clarification, and then I'm going to explain these 2 kinds of structures. I call them a target-driven and a method-driven logic. Logic is not here just means like a general schema that you can instantiate in various contexts, nothing more than that. I'll illustrate it by talking about the dark matter searches, and then I'll draw some implications. Okay, terminology. So let me clarify some of the concepts that I'm going to use. Some of these have a lot of connotations with them already in the literature, especially in philosophy. And so what I want to do is just sort of like set out how I'm going to use them for today. So try to so that we're all sort of on the same playing field, right? All right. So first thing that I'm going to use, method. I'll call it a technique sometimes as well. A method is any activity that generates empirical evidence where that activity can be applied in various research contexts and to various targets. So let me unpack a little bit. The term activity, right, it's purposely vague because methods sort of span a wide range of different techniques, scientific practices across disciplines, across scales. It's sort of anything that can be found in the methods section of a paper, more or less. So maybe more useful will be to give some sort of illustrative examples. Think about things like using radiometric dating in archaeology in a particular way, using randomized controlled trials in medicine to test, I don't know, vaccines, using fMRI to map regions of the brain. That's the kind of thing that I have in mind here, right? A second term that I want to clarify is that of a target or a target system. It's that system in the world about which the scientist's research aims to generate knowledge, specifically to explore and model features and causal interactions of that target. Okay, so just give an example. This is, consider the neutron. The target is the neutron, right? It's described by particle physics. It's made up of an up quark, 2 down quarks. It has mass, it has a magnetic moment. It undergoes free neutrons decay. That's also part of that description of that target. The full description of the neutron actually allows you to conduct different kinds of measurements for the lifetime of the neutron, how long it takes for it to undergo the decay. And so, fun illustrations because they move. So there's 2 kind of experiments that are currently happening, and these are 2 different types of methods that are used to measure the neutron lifetime. In one case, on the left, you trap a bunch of neutrons in a bottle, but it's more a gravitomagnetic trap. You wait for a while, and then you count how many there are left. In the other, which are called beam experiments, you get a focus beam of neutrons, and then the decay products get trapped alongside the beam, and then also counted. So these are just 2 different methods that are used to study the same target. All right. So hopefully that clarifies a little bit. Okay. Let me return to the main question, namely, how have physicists justified their choice of methods in the past? And for the neutron lifetime experiments, and for, I think, many, many experiments in science, this usually happens through what I call a target-driven logic. And so let me give the general schema, and then I'll give a quick implementation of it to sort of illustrate it. So here we go. We have a target system T with known features A and B. One more terminological clarification. When I say known, what I mean by that is these features are part of an empirically well-confirmed model of that target, right? Like we have a lot of empirical evidence that seems to support that description of the target. Okay. Method 1 uses feature A of T to uncover potential new feature X. Method 2 uses feature B of T to uncover potential new feature X. Method 3, clickers. Method 3 uses feature C of T to uncover potential new feature X. And then we get, since methods 1 and 2 use features that T is known to have, while method 3 uses features that T is not known to have, the preferred methods to uncover potential new feature will be methods 1 and 2, and you leave 3 out of consideration for now. So why do I call this target-driven? Well, because the justification here for why you think an experiment will be effective, why it's going to run in the first place, is appealing to pre-existing models of the target, right? It's that description that's like the main component of why this justification is supposed to work. So let me implement it a little bit. Again, the neutron measurements. So given the neutron, with all of its properties, bottle experiments trap neutrons through their mass and magnetic moment, count the beta decay products at various time intervals. Beam experiments use a focused neutron beam. And then optical microscopy uses a minimal resolution of the order of 10 to the minus 7 meters to magnify optical features of small objects. And obviously, bottle and beam experiments are using features that you know the neutron has, so both can be used to measure the neutron lifetime. Optical microscopy is working at length scales that don't apply to the neutron at all, so I don't think anyone will try to measure the neutron lifetime using an optical microscope, right? And I know this example of optical microscopy is a bit contrived, but my hope is that it at least conveys the structure of this target-driven logic that I have in mind here. Right? You select methods based on pre-existing knowledge of the target and on whether or not the target has, and whether or not the methods are latching onto features that you know this target to have. So far so good, I hope, and I hope that this seems like a reasonable way of sort of justifying choices of experimental methods. Okay. But of course you hear me coming. The problem is that the target-driven logic doesn't always seem to be available. Right? In fact, especially in cosmology and certain branches of astrophysics, it's hardly ever the case that one can appeal to the target-driven logic because you just don't know enough about the target. So here's a really accurate representation by XKCD of the current energy density of the universe. So for 5%, 5% consists of everything we know, everything we see, all the atoms in your body, our galaxy, all the stars and dust and planets within and outside of our solar system. For the rest, we have no freaking idea, right? We have no freaking idea about what they are, although we have very good reason to believe that they actually are there. And so, to push the point even more, consider dark energy, which is, so consider dark energy. Here's a quote from the Dark Energy Task Force, their report. This is from 2006, but as far as I can tell, correct me if I'm wrong, not much has changed with regards to this since 2006. So what they write is, although there's currently conclusive observational evidence for the existence of dark energy, we know very little about its basic properties. It is not at present possible, even with the latest results from ground and space observations, to determine whether a cosmological constant, a dynamical fluid, or a modification of general relativity is the correct explanation. We cannot yet even say whether dark energy evolves with time, right? And so this looks pretty dire for the target-driven logic that I just explained. But it doesn't seem to be that scientists then just stop doing science, right? And don't try to make progress on these kinds of questions, right? The atom interferometry experiments, although, again, I'm very curious to hear why it's not working out, but at least there was an attempt at, constructing this experiment that was gonna probe more features of dark energy, for example. So how do these work? How do these justifications then work? Well, here's an alternative way of justifying these experiments.
Sorry.
Yeah, sorry.
Sometimes you use the word dark energy, sometimes you use the word dark matter.
Mm-hmm.
Are you doing this purposely? Because
I'm using them as two separate examples, yes.
right.
Yeah.
Which experiment are we using to look for dark energy, not dark matter?
So there were atom interferometry experiments that were looking for evidence of chameleon fields that could sort of constitute dark energy. Yeah, at UCLA. This was happening. Yeah.
Okay, may I remind my statement in my previous talk? No, I would say what they used actually they check not dark energy in the dextrans, they check some models of which modify gravity at small scales. It's completely so. As I said yesterday, the method of measuring the properties of dark energy is taking as the universe as a whole, the test particles, and look how its properties evolve with time.
Yeah, so I don't think I disagree with you. And in fact, I think what I'm going to say next is... Oh, sorry. I don't think I disagree with you. I think, in fact, what I'm going to say next is going to, hopefully clarify that, right, the structure of justification for these experiments builds in a lot of assumptions, but I'll explain that now, yeah. So, given a target system T, we start again with the structure. So given a target system T, method 1 uses feature A of T to uncover potential new feature X. Method 2 uses feature B of T to uncover potential new feature X. Method 3 uses feature C of T to uncover potential new feature X. So it's almost identical to the first 4 of the target-driven logic, except for the first one, right? There's not much detail in the description of the target. And so that means that the rest of the structure is going to be different. Sorry, it didn't all fit on the slide without changing the font. So now we have conditionals. If T has feature A, method 1 can be used to uncover new feature X. If T has feature B, method 2 can be used to uncover new feature X. If T has feature C, method 3 can be used to uncover new feature X. And because we're now dealing with these conditionals, of course, the next question is, well, which antecedent are we going to trigger? It's possible and plausible that T has features A and B, but it is either impossible or implausible that T has features C. And then we end up, again, with sort of similar conclusion, right? So why do I call this method-driven? Well, because unlike for the previous one, the target-driven, here the justification of the method choice is primarily appealing to features the target would need to have in order for a particular experimental technique to be effective. but without there actually being independent reason to believe necessarily that the target actually has those features, right? And so the reason why definitely this last premise is here is that in order to sort of use this kind of justification in a responsible manner, you at least require the assumptions that you're going to make to be possible, but hopefully even plausible. And I'll give examples of plausibility arguments. Although I think Richard also gave some, but I think we disagree on the status of the arguments that he provides. Yeah. Okay. So let me now give again an example of how this is, so this was sort of the general structure of it. I think it's somewhat prevalent, so here's some of the examples, the dark matter searches that I'm going to talk about. The dark energy searches used to be, but they've changed. There's some, the 1980s cold fusion experiments are sort of an interesting sort of weird misapplication, and I think some of the dumbhole searches, these analog black hole experiments also sort of qualify. So, but let me focus on the first one for the remainder of the talk. So, dark matter searches. Once again, Jeremy Butterfield's pleasure principle is going to appear because I'm going to tell you something that you've all already known, namely, how is, what is dark matter, or what do we know about it? And I'm going to give a very quick description of it. So, the target needs to be somewhat defined, and that definition comes, unsurprisingly, from cosmology and astrophysics. And here's again the pie chart in a slightly more specified form. So dark matter, 26% of the energy density of the universe today. And here's a quick summary. It's a form of non-baryonic matter. It acts gravitationally. There's strong upper limits on potential couplings to standard model particles, as well as on the self-interaction cross-section, right? And that definition is based on evidence from a wide range of scales. So arguably the first evidence for dark matter came in 1933 when Fritz Zwicky was observing the coma clusters and was determining the velocity dispersion in the coma cluster. But probably, even though Zwicky's now sort of agreed to be the first to raise this possibility of dark matter, probably the most convincing and widespread acceptance for dark matter came from Vera Rubin's galaxy rotation curves. In 2006, we get the bullet clusters where the author, or it was a bit earlier, I think the publication was 2006, but the paper was early on arXiv. The authors here call it direct empirical evidence for the existence of dark matter, right? So the bullet cluster where you have this merging event of the two clusters. Then on even larger scales in cosmology, we have structure formation and the CMB. Okay, so again, from all of these sources of evidence and some more that I haven't even mentioned here, we get this sort of description of dark matter. But of course, it's remarkably thin, right? It tells us that dark matter is mass, but it doesn't, apart from that, it tells us mostly what dark matter can't be. And so, again, XKCD gets it right. The space of possibility for what dark matter could be is very, very large, I guess, aside from the things that have been excluded by buzzkill astronomers. So we have a very large space of possibilities for dark matter candidates, and this is sort of where the story becomes really interesting, right? Because the description I had up just a little earlier is that was a very, very thin description. It doesn't really tell us a lot about the additional features of dark matter. But the things that, for example, particle physicists are, I know, the longer you look at it, the more entertaining it gets. It's really true. But space cows is one of my favorites. Or pyramids. But more seriously, though, like the things that particle physicists, for example, are interested in when looking for dark matter are exactly the features that are not included in that definition I had up here before, right?
Excuse me. An important, a very interesting possibility, which is very widely discussed now, and which I don't see in your list of primordial black holes.
Sorry, so the possibility of dark matter being constituted by black holes?
Yeah.
Primordial black holes, yeah. Yeah, no, that's fair. So I think I didn't include it here because I think it's one of the possibilities, but it's also not something that we currently accept as an accepted definition of or it's a possible candidate, but it's not sort of something that the cosmological and astrophysical evidence currently, like,
But there's no evidence
As well-
neither for the others.
no.
You know,
Our examples, they're
Sorry,
gravitationally flat space cows. I mean, they're small.
Sorry, this cartoon is not supposed to be scientifically serious. But fair. I will let XKCD know that they got it wrong. It's very fair what you're saying about the primordial black holes.
I would say in some sense it's just the opposite, that all this possibility they are not, do not follow from existing standard model. But primordial black holes is just the opposite, it, in some sense, follow the Einstein gravity.
Yeah, so, okay, so I think, again, I don't think I disagree with you. I think what I'm trying to indicate here as what is currently, I was just focusing on what is currently accepted about dark matter, like what's sort of commonly agreed upon. I think with regards to what dark matter is then constituted by, right, you might prefer primordial black holes, and, you know, XKCD, I guess, it only gives a subset of the possible
No,
candidates.
but can I say something?
Yeah.
In the community today,
Yeah.
the two candidates that people discuss are axions and primordial black holes.
Yeah.
So it is within the very acceptable candidates within the cosmological community. So.
Yeah. No, again, I have no problem with it being a very acceptable candidate. I will say, for the remainder of the talk, I should already preface this a little bit. I am going to focus on WIMPs just because they've been historically the prime candidate. I'm well aware that WIMPs are very much in trouble right now, but for the philosophical analysis, it's a little more accessible to look at what the historical sort of experimental justifications have been. I don't think that my philosophical argument depends on the WIMP case. It's an illustrative example, but I think you could make the same case that I'm going to make for things like axions or primordial black holes as well.
Sorry, just also some clarification. When all these black holes are ruled out by the evidence, I think all this evidence, all the argument applies if you think all of dark matter is represented by black holes, but a fraction of the dark matter being represented by black holes is not at all ruled out in that drastic way.
Yeah.
Okay, then one more comment about the recent result. It's possible to have all that matter in the form of primordial black holes, but with masses between 10 to 17 grams and 10 to 23 grams.
Okay. Okay. Although I find this really interesting to talk a lot about possibilities for dark matter candidates and what the current state of the art is, maybe it's more useful if I take this XKCD comment off the slides so that we can stop looking at it, and then I'll just finish the talk, and then if you want to take it up again, I'm happy to do so. Okay, let's just do that. And again, with the already prefacing that I'm going to talk mostly about WIMPs, even though I'm aware that they're sort of, no longer the main accepted candidate. But yeah, so I gave you sort of a description of a target. And now, what I want to do is talk about some of these experiments that I mentioned in the beginning that are looking at dark matter, or looking for dark matter candidates. And I'm going to focus first on direct detection experiments. These have been around since the 1980s and sort of continue still to be a main player, if anything, in excluding the WIMP hypothesis, right? So here's sort of the representation of different, very high-level representation of different kinds of searches for dark matter particles, and the arrows indicate the direction of time, the direction in which you have to read the diagram for the different searches. So for direct detection, we're reading it bottom to top. Chi is dark matter, F is standard model particles, so we get in direct detection experiments, basically we get a scattering of a dark matter particle from standard model particle, and then hopefully that scattering deposits some kind of signal that can be detected, right? That's the hope for direct detection experiments. And so what I want to show you is that these experiments are justified through this method-driven logic that I gave you. And I'm going to give you the argument first, and then I'm going to give some background on each of the premises. So, given dark matter as described by astrophysics and cosmology, right, that was sort of the first part that I talked about, neutrino detection techniques or experiments use the weak coupling of neutrinos with an extraterrestrial origin to detect their presence by their deposited energy and scattering events of neutrinos. Sorry, there's something wrong with the grammar there, but basically by the deposited energy. Okay. If dark matter particles, I should stress this, are weakly interacting, have a mass of the order of 100 GeV and exist stably in the galactic halo, detectors similar to those used for neutrino detection can be used to search for signatures of dark matter particles existing in the Milky Way halo. Based on astrophysical evidence and the WIMP miracle, it was plausible that dark matter particles were weakly interacting, have this mass of the order of 100 GeV, and exist stably. So detectors similar to those used for neutrino detection can be used to search for signatures of dark matter particles. So again, let me now run through it. So the first premise just refers to what I described in the description of dark matter, what we get from astrophysical and cosmological evidence. A very thin definition. Leaving room for things like primordial black holes, axions, WIMPs, the like. Maybe not space caps. Neutrino detectors experiment. So let me now talk about the neutrino detectors and these neutrino detection experiments. So what was this focus? Well, think of Kamiokande. So this is Super Kamiokande, the successor of Kamiokande, which was this was basically a giant vat of cleaning fluid or super pure water underground. And one of the things that Kamiokande did was find solar neutrinos. And so the way they did that was exactly by this kind of scattering of these solar neutrinos and then finding, detecting the signal of that, okay? And so that's the method that's under consideration here. Okay, the conditional. If dark matter particles are weakly interacting, have a mass of the order of 100 GeV, and exist stably, right? That's what then these similar techniques to neutrino detection techniques can be used to look for dark matter. And so this is where the assumptions are being made about the dark matter particle. And so I'm going to read papers from the 80s. These are not state-of-the-art papers, but 80s, right? Okay. So in the 80s, when dark matter became sort of widely accepted, it was this parallel with neutrino detectors that particle physicists initially appealed to in the development and justification of these direct detection experiments. So here's one example of a paper by Goodman and Witten. They say, dark galactic halos may be clouds of elementary particles, so weakly interacting or so few and massive that they're not conspicuous. Recently, Drupi and Studolsky proposed a new way of detecting solar and reactor neutrinos. The idea is to exploit elastic neutral current scattering of nuclei by neutrinos. The principle of such a detector has already been demonstrated, and then in their paper they calculate the sensitivity of the detector to various dark matter candidates, and that's like the rest of the paper. Similarly, Wasserman, which was the other main paper who sort of did this work, recently a new type of neutrino detector, which relies on the idea that even small neutrino energy losses in cold material with a small specific heat could produce measurable temperature changes, has been proposed. The purpose of this paper is to examine the possibility that such a detector can be used to observe heavy neutral fermions in the galaxy. Such particles, it has been suggested could be a substantial component of the cosmological missing mass, dark matter, and would be expected to condense gravitationally, in particular into galactic halos. And so in both cases, you see immediately that they draw the explicit parallel with these neutrino detection techniques, right? So both papers are explicitly making this sort of like, well, we have neutrino detection techniques, maybe we can use them for dark matter. And so how do they know that their assumptions that they were trying to make about dark matter were somehow possible or plausible? Well, at the time, for that, a lot of the direct detection searches, definitely those proposed in the 1980s, were appealing to constraints from cosmology and astrophysics and to what was possible within these constraints. So for example, they immediately excluded neutrinos themselves as dark matter candidates, right? So here's a review article. I won't go through it for the purpose of time, but basically hot dark matter was immediately considered at least less successful than cold dark matter already in the 1980s. But even more strongly, right? It wasn't, at the time, it wasn't just considered possible that dark matter had the specific properties it needed to have for these directed techniques. They even gave some sort of plausibility argument for it, which was exactly the WIMP miracle. And I'm sure that most of you are familiar with this, but the basic idea behind the WIMP miracle is that if you introduce weakly interacting massive particles, so WIMPs, in the early universe, in the standard scenario of Big Bang nucleosynthesis, and then you just wind the story forward, the abundance of dark matter that is the abundance of dark matter today that's predicted by that theoretical story matches up exactly what we expect based on observations, right? And this is sort of a happy miracle called the WIMP miracle, which is why WIMPs for a long time, or part of the reason at least why WIMPs for a long time were considered the favored dark matter candidate. Of course, recently it's come under serious pressure, right? And now axions are much more favored. And so, based on all of the previous information, we end up with this conclusion, or in the words of the same review article, the exciting possibility exists of detecting WIMPs in the laboratory. Okay, good. Okay, so hopefully this is sort of, I've tried to convince you at least that these direct detection searches provide this kind of example of what I call a method-driven logic. So let me now get to some of the implications and sort of a summary of where we've ended up. So what I proposed initially was that there are sort of two logics at work in justifying particular method choices, a target-driven logic and method-driven logic. The target-driven logic appeals to pre-established knowledge of the target to argue that a particular method will be effective. The method-driven logic appeals to what features a target would need to have in order for a method to be effective. And so the method-driven logic, I think, is particularly important in contexts where the knowledge of the target is very thin, like the case of dark matter, say. And so I've tried to illustrate this method-driven logic through the dark matter case. But let me now return to some of the issues in the beginning. So first, hopefully this sort of provides a general story to explain why these experiments are considered, possible and good ideas in the first place, right? Like, initially they seem sort of implausible, trying to answer cosmological questions in a lab setting, but it turns out that there's, a reasonable structure behind it. But there's also more to it. So here again is the Feynman diagram, and I just talked about this arrow, but of course there's two more on here. And so one of the other arrows is the production experiments, where this is what happened at CERN, for example, where the attempt is to produce dark matter particles, or at least produce a type of mediator that could couple two dark matter particles. It can be used for different things. And so, again, I won't go into too much detail, but I do think that this type of experiments are also justified through what I call this method-driven logic. But importantly, the kind of assumptions that are required to justify the production experiments that are happening at the LHC are different than the ones that are required for the direct detection experiments. They're not the same, right? For the accelerator experiments, the focus is on the coupling of these unknown particles to standard model particles to detect either unknown particles or unknown couplings that could be candidates for dark matter. And so either there's assumptions that either dark matter is made up out of supersymmetric particles, but again, it's come under pressure, or at least there's an assumption about a type of unknown coupling to standard model particles, right? And so there's different assumptions that are being made here. Now, you might not be worried about this, right? Especially if you're a philosopher of science and you're aware of the robustness literature, or like literature on multimodal evidence. So just to give you some background, the idea behind multimodal evidence is, so multimodal evidence is the situation where there are different lines of evidence that come from different experiments, where these experiments have different kinds of systematic errors associated with them, right? And so there's large discussion in philosophy of science on multimodal evidence, but in general, there's a couple of claims that are more or less consensus, although it's always dangerous to say that with philosophers, right? But one of the claims that's sort of broad consensus at least is that sometimes, multimodal evidence is necessary to achieve certain scientific goals. In the case of dark matter, so if you want to answer certain questions, you just need different kinds of experiments, right? And so in the case of dark matter particle searches, that's definitely the case. The sensitivity of the production experiments is complementary with the sensitivity of direct detection experiments. So here's an example, like the different colors indicate different kinds of experiments. So I can't tell exactly, it's too small on here. But anyway, different colors represent different kinds of experiments. And you notice that, so when I say different kinds of experiments, I mean production, direct detection, indirect detection. And you notice that there's like, wherever color, a different color indicates different high experiment having like the best sensitivity at that region. And so you notice that these different kinds of experiments are actually, you know, most sensitive in different regions, so they allow you to probe more of parameter space. So that seems good, right? Because it's kind of necessary, given that there's so much of parameter space to explore, you kind of need a lot of different techniques to try to explore it. Another consensus in philosophy of science is that multimodal evidence is a good thing because of the reason that I mentioned earlier. The idea is that if you have different experiments with different systematics that all somehow give you the same result, then it becomes a lot more plausible that that result is not due to systematic errors, but rather is somehow revealing a real physical effect. So the determination of Avogadro's number is one of the favorite examples in history and philosophy of science that sort of illustrates this case, right? And so I think this also applies in the case of dark matter in the sense that the image I had before came from the LZ design report. And in that same design report, and I forgot to put the quote on here, I just noticed, but in the same design report, they sort of say, claiming that dark matter has been found, or dark matter particle has been found, will require that we're able to find that particle not just in direct detection experiments, but also through other types of experiments like production or indirect detection experiments, right? So they're sort of instantiating this kind of idea, like we need multiple independent kinds of experiments to all find our dark matter particle in order to believe that we've really found it, right? Because it's so elusive. And I think, although this seems a typical sort of example of the robustness argument, this is where there's a little bit of trouble that comes up in the context of these method-driven experiments. Particularly, I told you that the different kinds of experiments make different assumptions about the nature of the dark matter particle. And as a result from that, they also constrain, the results constrain different sets of parameters. So in the case of direct detection experiment, the interaction cross-section and the dark matter mass is being constrained. So you have two free parameters. In the case of production experiments, particularly the ones that are looking for mediator particles, I think, what's being constrained is 4 free parameters, which is the mediator mass, the dark matter mass, the coupling at the standard model vertex, the coupling strength there, and then the coupling strength at the dark matter vertex. And so the problem is that because of the different assumptions that were made about the nature of dark matter to get these experiments going in the first place, in order to then compare the different results with one another, additional assumptions need to be made to translate the different results into the same language, right? And so here we see that the standard robustness results, or the standard robustness argument that philosophers of science seem to think is a good one, it becomes a little more difficult to actually apply it in the case of dark matter. So, yeah. And with that, I'm going to end here. Oh. Let me also, you can't read it, sorry, the resolution is too low. It says, after the discovery of antimatter and dark matter, we have just confirmed the existence of doesn't matter, which does not have any influence on the universe whatsoever.
Thanks. So I guess my question is regarding that stuff that you said about multimodal evidence at the end.
Mm-hmm.
You focused a lot on particle searches, but
yeah.
I guess obviously there are we have lots of lines of evidence, independent lines of evidence for dark matter. Mm-hmm. What's your take on the reason why there's this focus on the necessity of particle detection, given that arguably we do have multimodal evidence already?
Okay, so I think it depends on, so we have lots of multimodal evidence for the existence of dark matter. I think what the direct detection and production, the particle searches are looking for is, well, given that there's this type of unknown matter that has all of these effects in the universe, what is the fundamental particle nature, if it is a fundamental particle, right? It could also be the black holes, things like that. So they're answering a different kind of question, I think. So there's lots of multimodal evidence for the existence of dark matter, but not, but the thing is that the question that's being answered by these direct detection and production searches is a different kind of question, I think. Professor Stern.
Okay, I just, I would say from the methodical point of view, I would say that indeed, I think we have complete agreement, and indeed different experience, they investigate simply different properties. So my remark is simply because I noticed that there are many statements of other people which you cited regarding experiments were actually 30 or even more years ago. So much has been a change in experience since that time. And so I would like just make a proposal to use your method to consider a question which is actually only remotely related to irregular gravity, but it has direct relation to elementary particle physics, and which is actually actively discussed and explored experimentally at the present time, is the possibility of a fourth so-called sterile neutrino electron volt with a mass of the order of or slightly less than electron volts. So, and here we have exactly the same the situations which were mentioned. First, from the standard model that there is no such neutrino, from standard cosmology, assuming a classical Einstein gravity also that there should be no such for still neutrino, but from the existing experiments there are some hints in some experiments when okay that still this for neutrino exists, and so actual experiments are going on actively. So I think it's a good new field for using your philosophical approach.
Yeah, thank you. Sorry. Thank you. Yeah, no, that's a really interesting case, and it's one like I haven't really looked at that many other types of searches, but yeah, that's a really interesting example where it sounds like it could possibly also apply. I think. Okay. Chris.
Thank you all. That was very interesting and inspiring. I have a question about multimodal evidence as well. There's something I can't quite wrap my head around. I think it's hard to disagree that it's a good thing in case we can get it.
Yeah.
But I find it ultimately unconvincing that it's necessary.
Oh.
Surely, at best, it's necessary in some cases. But surely there are also things we could just detect in one and only one way, directly, with a satisfactory statistical significance, and we just got it, and that's it. And then it seems like it's not necessary.
Yeah, sorry, that was careless wording on my part. You're absolutely right. I think there are cases where it is necessary just because of the practicalities and particularities of that given case. But sure, there's definitely things where like, there's only one way of finding it, and that's it, and it's good, you know? Yeah, I think that's really right, thanks.
Yeah, when you gave the list of examples of method-driven cases, the last point was the dumb hole, which seems to be a very different case where actually you don't test something the target might have, but you just shift the target. So in including that, it seems that you considerably broaden the concept of method-driven cases. So my question is, why do you include this?
So, okay, I know there's people here who know a lot more about this, so I'm interested to hear your thoughts about it. The way I think it works in that case is that The target isn't black holes. The target is this existence of Hawking radiation as a universal phenomenon, I think. And so in that case, I think, yeah, is that correct? Sorry, this is one I'm going to have to look through it again. I'd be happy to talk about it more in detail because off the top of my head I can't fully reconstruct it immediately. Sorry, yeah, but it's a legit question.
Yeah, so just one other thing that I think that wasn't, that occurred to me while you were speaking, but I think you weren't emphasizing, that I'm curious about your thoughts on. It seems like in the method-driven cases, so in the target-driven cases, you're trying to draw an inference about whether or not the target system has property X.
Yeah.
In the method-driven cases, you're going to presumably be in a position to draw inferences about both X and A,
Yeah.
or X and B.
Yeah.
And that seems like a pretty significant difference.
Well, yeah, you're sort of from the get-go in a different epistemic situation, right? In the one case, you already have empirical evidence for whatever you're going to assume about the target, or like whatever properties the target has. In the other one, you don't. So yeah, it's definitely it has different implications for how you're going to interpret these results. I think my current position on it is that in the case of, if you don't find it, right, like in the case of the WIMP direct detection experiments that have just been failing constantly, or failing to find anything, but being very good at putting constraints on like where WIMPs are not. So in these kinds of negative results, you actually can make very strong inferences about, okay, the assumption that I made about the target is completely wrong, and it also doesn't have all of these other properties that I was hoping to find with it. I think in the case of the positive, like suppose you do find a positive direct detection result, I think it's a lot less clear about whether or not you can actually make this assumption, make these conclusions about the antecedent, like the assumption that you were making about the target.
So you wouldn't infer from a successful, nuclear recoil experiment or something like that, not only, for instance, the mass of the WIMP, but that it is weakly interacting?
Well, I think so. I think what I would infer is that there's some kind of signal that is weakly interacting, that comes from something that is weakly interacting, and that there's a particular mass. What I think is murky is whether you can then infer that that's about your original dark matter, like that's about the original target that you were setting out to investigate, which is dark matter. I think in that way it's
But
murky.
then presumably you want to go and investigate that.
That's why you need the that's why you need the alternative experiments to then find it, but then there's additional worries there. Yeah.
Is that a finger?
It's a question.
Oh, hang on. Please.
Yeah, so very interesting talk. I think my question was just that it seems like there's a common ingredient in the two methods, which is the concern is about accessibility to the target systems, and in one case it's more of a hypothetical. So, I mean, as you're going through it seemed as there's sort of a target-driven logic, and then I was tempted to, and I'm curious if this is on the right track, so there's more of like a hypothetical target system logic. So it's sort of, there's a more radical version of a method-driven logic, perhaps, where you just say, I have a method, I'm just going to keep using that, that's all I'm going to use, right? Or something where you just say, I only have faith in randomized controlled trials, or something like this, where you just say, I'm gonna have this method, that's the only way I'm going to adopt that's the only way I'm going to investigate matters in this domain. And so that's when you first started talking about method-driven logic, I thought it could be something that radical, but it seems more like this hypothetical, you make hypotheses that would give you access to the target system, but then it actually seems quite close to the...
So I guess the way I could translate it is the two are on a spectrum. Does that seem to sort of get at your concern? I think that's fair that they're on sort of a spectrum and like you can land at different parts, which is how much evidence do you have about what you're going to assume about the target, and of course that comes in levels of degree, right? I think the case that I'm talking about is one where there's like, the neutron lifetime case versus dark matter seems to be sort of two more extreme versions of that spectrum where these concerns really come out. As far as the situation where you're like, I only have this one method and I'm going to use it for everything, Well, it seems an interesting attitude, let's say.
I'm just saying that
Yeah.
was when you started
No.
talking about method-driven, that seemed like, yeah.
I think, just for the sake of argument, I think if you want to do that approach in a responsible way, somehow the actual specific justifications you're going to offer are probably going to collapse into either one of the two that I mentioned anyway. I'm not sure, this is like just from what you're saying, but it seems to me like if you want to do it responsibly, yeah.
Okay, we have a question.
Thank you for your interesting talk. My concern is similar to that of Chris, and I think robustness is not necessary to believe in the existence of something. It's true both in science and in ordinary life. In science, the detection of neutrino or Higgs boson or up quark, these are all cases of something that we believe in their existence without robust evidence, in the sense that we have multiple models. And in ordinary life, I can say that these class exist without have different method of detection of it. Only because I have good evidence to see this class, so it exists. I think the robustness is more consistent with biological context, you know. And some philosophers of science, for example, Vincent, applied robustness to biology, and that is more consistent with biology.
I think this was sort of a little too quick on my part. I think I want to separate out the multimodal evidence and the robustness. When I say multimodal evidence is a good thing, I mean because it allows us for the construction of robustness arguments. So that's sort of like the one half of those two claims. When I say multimodal evidence is necessary, I should have said multimodal evidence is sometimes necessary, often in cases like biology, because of the complexity of the targets that you're dealing with. I do think that it's not just constrained to biology, right? I think when you're dealing with these kinds of parameter spaces where it's really vast, and you can't expect one particular technique to sweep all of that or to like probe all of that, that's sort of an example where it seems kind of necessary to start employing these different kinds of experiments. But again, I don't think that it's generally the case that it's always necessary to get multimodal evidence. In fact, I think you give good examples of cases where that's not true. Yeah.
Okay, just a comment and a question. A quick comment is, we should always remember that, you know, extraordinary claims require extraordinary evidence, and your class does not seem so extraordinary. So, on the other hand, the question I wanted to ask is, and I must confess I haven't been following the developments in the last couple of years, but for a while there was a strong controversy regarding this DAMA experiment, where you know, workers in the field are very, very convinced and have made very strong claims. They have positive detection. Does your approach or your method or your ideas have something to say about that particular situation?
Well, even independent of this talk, I have lots of thoughts about the DAMA experiment. But I think just for the contents of this talk, so I mean, so let's be as charitable as possible for DAMA and sort of ignore the fact that they haven't, as far as I'm concerned, as far as I know, they still haven't released their data, right? Like, they just claim they have detected it, but they haven't released any of their data. Does anybody know? Okay, I think that's still the case. So suppose that, you know, they've released their data, it seems like a credible signal, it seems like somehow there's something interesting there. I think even in that case, we'd want the LHC or a different kind of experiment to start looking in that same region to confirm that that signal is there. And also get different direct detection experiments to confirm that that signal is there for the robustness case as well. So yeah, even if you just have DAMA that gives you this positive signal that seems to suggest something like particle dark matter, I think in order to claim that it actually is a detection of particle dark matter, it would require more evidence, not just from DAMA, but additional experiments. Yeah.
Okay, let me only add to you that I think it's a general, not only philosophical but scientific statement which refers to Dhamma. The only the thing that we can say that the results were not confirmed by other independent experiments. And the same refers to another topic which you mentioned, called fusion.
Okay, last question.
So actually my kind of original question was you addressed in your answer to Chris about the spectrum, because that's the way it looked to me. I mean, it's sort of characterized by plausible to implausible. I also sort of had in the back of my mind how far you were willing to sort of think of this in a kind of Bayesian way. But that leads me to actually a thought about how there might be a kind of distinction of kind rather than just qualitative, which is I take it in the target-driven system, you're thinking that from a Bayesian point of view, the sort of priors that are giving you kind of plausibility to the properties of the target are coming from previous sort of experimental evidence, and so you actually have confirmation of that. But what's happening in the method-driven case is you don't have sort of any empirical confirmation, and so those priors are the kind that are just coming from who knows where in a sort of Bayesian kind of picture. So there is a sort of difference there about where, what's making the the assumed target properties kind of plausible to you in the first place, maybe. But I guess I was just kind of interested, where those priors are. That's sort of where the question was coming from. Is where are those priors coming from in your sort of analysis, if you're thinking of it in a Bayesian way?
Yeah. So. So I think I'm sort of, I'm now at a 10, I'm wondering whether I'm on the spot, currently changing my mind because of what you said. I think I have a concern, right, initially what I was gonna, so let me tell you the thought process because I'm where I'm at, right? Initially what I was going to say is, well, maybe those priors don't come from just about anywhere, right? Because things like the WIMP miracle seem to give sort of a nice story. But then again, I'm worried about just putting that all into priors and not actually distinguishing in the content of those priors, because I do think that there's an important difference, like you indicate, of sort of where they come from. So, yeah. I'm not so okay. So I guess we should go to coffee break. But I don't think I'll just say it's time for coffee break.
Well,
no, but it's very interesting.
If your answer is that's a kind of meaningful question, I guess then that's sort of helpful for seeing how
No, definitely.
how
Thank
this
you.
is working.
Definitely. Thank you.
So we are out of time. Thank you, Siska.